Hello, welcome back to ECE484, Fall 2021. Again, I apologize for last lecture where I couldn't do it live. I had to pre-record it, so it won't happen again. I returned term test 2 yesterday. Should have received your marks. Let me know if you did not or if you had any issues with that. And yeah, so we continue. We continue with our regularly scheduled program, if you will. Okay. So last class, we essentially started our control design in discrete time, right? And the setup is as shown in this picture here, where we control, or we will try to control, a discrete time plant. And that discrete time plant is always generated by taking the step invariant transformation of a continuous time plant, okay? So that's the picture here. And we started looking at design technique, and the first one was pole placement. And the good thing, or the bad thing, depending on your point of view, is that there's not much more to say about pole placement in discrete time than what we've already said in continuous time. It's essentially exactly the same. The formulas are the same, the idea is the same, the conditions under which you can do pole placement are the same. Nothing really changes. Limitations are the same, I should say. Nothing really changes. The only kind of small tweak is that for a discrete time system, picking desired pole locations, i.e. roots of the closed loop characteristic polynomial, it's not clear how to do that. We don't have good intuition about where the poles should be in the z-plane, okay? And so what we did, or what we talked about, is to choose your desired z-plane poles in this way, right? So what you do is you pick a lambda, which is in the good region in the s-plane, and then you map it over through this exponentiation. And the justification for that, the motivation for that, is because we know that when you do C to D, poles of the continuous time system get mapped to poles of the discrete time system through this mapping. Okay? So other than kind of this extra step in picking the pole locations, there's really not much more to pole placement in discrete time. Okay, so we'll continue from there. Let's do an example of picking z-plane locations. And so this is example 821 in the notes. Okay. And in this example, we are just going to show how the method or the process of how we get desired pole locations for a discrete time system. Okay, so consider a sample data setup. Right, so a continuous time plant being controlled by a discrete time controller with a third order plant. Okay. Take our sampling period. TP 0.1 seconds, and it's not pathological. Right? Meaning that the discrete time plant that we get will also be third order. We won't lose any essential behavior of our continuous time system. There won't be this aliasing. Okay. Our specs for the closed loop system. Okay, picking pole locations really comes down to transient specifications. So in this case, we'll talk about stability, of course. We'll say that the settling time for the step response should be less than 3 seconds. And thirdly, we've been told that we want enough phase margin to get good robustness. And so in particular, we were told that we want a minimum phase margin of 50 degrees, again, for robustness, good stability margins. Okay, so remember the process. there was a 3-step process we talked about at the end of last class. Step 1 and 2 are exactly what you do in continuous time to get the good region. Step 3 is this extra step that we'll do for discrete time systems. So step 1 is to find, or characterize CG in the S-plane. Okay. Again, this is repetitive. You've seen this type of example before, but we'll do it anyway. Okay, so from this TS spec, we have that the good region, whatever it turns out to be, has to be contained in the set of complex number whose real part of S is less than or equal to -4 over the maximum allowable settling time, so -4/3. Okay, the settling time spec. From the phase margin spec, what do we have? We have that phase margin should be greater than or equal to 50 degrees. We didn't talk about it in class, but we have seen examples where we turn phase margin specifications into conditions on the damping ratio, which we then turn into angular constraints on our poles. Okay, and so we'll do that here. So this will imply that we want a damping ratio greater than or equal to 0.5. And again, we've seen this before, but I'll remind you that this is using equation 3.4, section 331. Okay, we've seen this before, but in any case, we know that once you have a damping ratio spec, you can turn that into an angular constraint. In this case, you get a theta max of pi/3, 60 degrees. And so our good region pi/3. Right, so we get this cone again with the top chopped off. All right, so therefore we have our good region. Did I make a sign error? Yeah, that's fine. Okay, there, intersect. Okay, and it's the usual picture. Let's draw it. Something like this, okay? This number here is -4/3. And this angle here is 60 degrees. Okay, nothing special. So step 1 is always that. Step 2, pick your desired pole locations inside of the good region. Now, we said this was a third order controller. So to solve pole placement, we're going to need a order of the plant -1 controller, so a second order controller. And so we need 5 desired pole locations. So in this case, n equals 3. So we need 2n minus 1 equals 5 desired pole locations. Assuming I'm doing a standard pole placement controller, right? I'm not requiring a strictly proper controller. Okay, so let's pick some. These are going to be the symbols for our desired pole locations in the S-plane. And I'll pick two dominant ones, as always. Okay, that might require a lot of control effort to place the poles so far to the left, but the 20 and 21 and 22. But our rule of thumb, again, is that they should be the non-dominant poles over there. So far, nothing new. This is exactly what we've done before, but step 3 is the new step. Is that we map to the Z-plane. Okay? And so our desired pole locations are going to be the pole locations from above, but multiplied by the sampling period. Remember, the sampling period here was 0.1 seconds. So the first one will become e to the negative 0.5, e to the j 0.01. And then e to the negative 0.5, e to the negative j 0.1. Okay, remember, t is equal to 0.1 seconds. Okay, and so on. You just keep mapping them over. And we get our desired pole locations. All right. So that's the point of that example, just to illustrate kind of the new aspect of our design procedure. Everything else is exactly the same. So notice in discrete time that dominant poles, so these are the dominant ones, are closer to the origin. Sorry, further away from the origin than the non-dominant. Right? Poles close to the origin are kind of fast dynamics in discrete time. Yeah? Further away from you are from the origin, the slower the poles are. Okay, so that's it. Pole placement, we can just add it very easily to our toolbox. And so again, following sort of the strategy we did in chapter 3, can we also incorporate some steady state specifications? And so we're going to talk about step tracking. Okay, so we're going to be given a continuous time spec. On the steady state tracking error. Right, that's the limit between the difference between the reference, the desired output, and the actual output of the plant. And we want this to be less than some ESS max. Right? What's the strategy in this chapter? Well, what we'll do is we won't necessarily satisfy that spec between the sample periods, but our aim in doing direct design is to satisfy it at least at the sample points. Okay? Given such a spec, in direct design, we'll view it, or we'll treat it, this as a spec on the sample instance. Okay? And so what we want is that this number in discrete time now should be less than the given spec. Okay. Is there any reason why you don't choose the non-dominant poles to be this? No, there's no reason. I could have chosen them to be all at -20. There was no reason. I mean, one of the things you've seen now at this point is that there is some iteration in choosing pole locations. So I just picked different numbers, but there's no reason. So the picture to keep in mind when we're doing this type of design is that if you have time here on this axis, our aim when we're doing, I mean, the whole thing about direct design is that we work with the sample points. So if this, for example, was KT, right? These are the sample points. What we're asking in steady state is that if this is our reference, R of k, we're not necessarily saying anything about what's happening between the samples, but at the sample points, what we want is our output y pass through the sample points. Now, in most cases, it's not going to look so as exaggerated as I've drawn it here. But keep that in mind, right? There is this intersample behavior which is not taken into account when you're doing this approach to direct design. Again, my suggestion generally is to use simulation to deal with that intersample behavior. There's theory that can deal with it, but in my opinion, it's not worth the effort learning the theory. Okay. So we basically going to break this step tracking spec into two cases, just like we did in continuous time. The case when we want zero steady state error, and the case where we allow some non-zero steady state error. So the first is zero steady state error, which as before we called asymptotic step tracking. Okay. So we have a reference, which is a step of any size. Okay, so there's our step input. Essentially by the internal model principle applied to a discrete time system by the discrete time internal model principle, which is exactly the same as continuous time. If the feedback loop is stable, right? And so for us, that means that the closed loop characteristic polynomial has all its roots with magnitude less than 1. And the product of the controller and the plant has a pole at z equal to 1. Why z equal to 1? Because remember that the z transform of our input, of the reference, sorry, is this guy, right? So the reference itself has a pole at z equal to 1, and that's the internal model principle. Always says you want a copy of the unstable part of the reference. So in this case, we want a pole at z equal to 1. Then ESS is equal to 0. Okay? And so from a design point of view, it's very much consistent with what we did in continuous time, right? There'll be a case where if the plant already has a pole at z equal to 1, just stabilize the loop. If the plant doesn't have a pole at z equal to 1, the controller has to provide it. Okay, so it's conceptually, it's exactly the same. Okay, except now instead of having poles at the origin and doing integration, we have poles at z equal to 1 and doing summation. Right? Remember that z equal to 1, is like a summer. We saw this example in chapter 6. Okay, so this suggests the same kind of stuff we did in continuous time. If P of Z has a pole at Z equal to 1, use regular pole placement. To design D of Z to meet transient specs and stabilized loop. Okay. Again, it's a little bit repetitive from what we've seen in chapter 3, but except now we're doing it in discrete time. 2, if P of Z has neither a pole nor a 0 at z equal to 1, right? We don't want the plant to have a 0 at z equal to 1, because then adding an internal model will result in an unstable pole 0 cancellation, and those, of course, are not allowed. So what we'll do in this case, we will choose D of Z to be of the form this form here. So in other words, we embed that pole at z equal to 1 in our controller, and then we design D1 for the augmented plant, just like we would have done in continuous time. And design D1 of Z using, say, pole placement on the augmented plant. Which in this case would just be given by the usual thing. Okay? And so, why is it, doesn't there need to be a Z in the numerator? So remember, the numerator plays no role in the internal model principle. It's the, if you remember, what we did is we take our reference signal, and what we've said before was that you take, I'll talk about it in the context of Z transforms, but we talked about it in the context of Laplace before. But you take your reference, take its Z transform. It'll have whatever numerator, it doesn't matter. But the denominator is what we're interested in. We factor that denominator into a stable part and an unstable part. Okay? And the internal model principle says that what we want is the unstable part of that reference, which is the roots in its denominator, which have, in this case, magnitude greater than or equal to 1. So the numerator of the reference plays no role in the internal model principle. So that was the case before. It's still the case here. And so, so we don't need we don't need everything about R. We just need the unstable part in the denominator. I mean, and this is consistent with what we did in continuous time, right? In continuous time, if you had a step of size R0, its Laplace transform would be R0 over S. And we didn't include the R0 in our internal model. We just kept it was the S that we kept. Okay. So I'm not going to do any examples of this in class because frankly, there's nothing new to say in terms of the examples. It would be a repeat of what we've seen many times earlier. I've done examples like this, and there are some in the notes. Okay. So remark, other reference signals can be handled in the exact same way. Similarly, just replace one over z minus 1 with 1 over, this is sort of what I was just saying, d plus r of z, where is the unstable part of r of z. Yeah, if the planet has a 0 at z equal to 1, you can't solve it, right? Same as I mentioned before, yeah, indeed. If the planet has a 0 at z equal to 1, it's not solvable. For the same reason. You get an unstable pole zero cancellation, the characteristic polynomial will have a pole at z equal to 1. So yeah, it can't be done in that case either. Okay, the other remark I want to say here is that if the continuous time system, P of S, already had in it an internal model of the continuous time reference, then when you do C to D, you'll still have that internal model. So if P of S has a pole at S equal to 0, so in other words, an internal model of R of S, then when you discretize, what happens? Remember, we just talked about where the poles go. C to D will have a pole at Z equals E to the T times 0, right? Which is 1. So internal model of R of Z. Okay, so the internal model gets mapped over. Okay, and to the point, to the asked, if P of Z has a 0 at Z equal to 1, asymptotic step tracking isn't possible. Okay. So, so that's all I'm going to say about that. There's not much different from what we've seen before, so you should be comfortable with doing essentially pole placement, which you've done many times, but in discrete time. I will spend a little bit more time talking about the case when the tracking error is, the maximum allowable tracking error is non-zero, because the equations are there, in this case, a little bit different. Okay, so let's talk about practical step tracking. This is when your maximum allowable error is positive. Okay, the same comments I made in chapter 3. When I say practical, it's not to say that asymptotic step tracking is impractical. It's just a way to distinguish the two cases between zero steady state error and non-zero steady state error. Okay. Okay, so we go through the similar sort of thing as before. So we've got our step. reference. And let's just suppose for now that we've designed a controller so that the closed loop system is stable. D of Z stabilizes the loop. Okay, we want to talk about tracking error, so let's look if we can use the final value theorem to analyze the steady state tracking error. Okay, so what do we want to check? Let's check this quantity, right? I'm looking at this quantity because if that quantity has no poles with magnitude greater than or equal to 1, then I can use the final value theorem, discrete time version, to figure out what the steady state tracking error will be. Okay, so I want to check if this thing is, I can use the final value theorem. Furthermore, just like in continuous time, what we're going to see is that this steady state tracking error will depend on the gain, the low frequency gain, the steady state gain of the controller. So let's see. Plug in the usual things. Okay, that times the reference. Okay, we do our usual things, put things over a common denominator. Denominator of the plant, denominator of the controller. Okay, so I've just plugged in the Z transform of R, and then I've written the same way we did in continuous time, our plant and controller as numerator over denominator, put everything over the common denominator, which is the characteristic polynomial, and this is what we've achieved, right? So nothing different than continuous time. These two terms will go away, and so we get over pi, okay? And because D stabilizes the loop, we know that the characteristic polynomial has no roots with with magnitude greater than or equal to 1. And so in particular, this guy, which is dp dc, is what we called sure by closed loop stability. Okay. So in other words, this quantity, z minus 1 times E times capital E, has no roots with magnitude greater than or equal to 1. So we can apply the final value theorem. Has no poles with magnitude greater than or equal to 1. The final value theorem can be used. Okay. And so when we do that, we get that ESS equals the limit as z approaches 1 of that quantity that we just computed above. Okay, so I'll remind you that it's that thing there. So I'm going to just plug in the expression. And so what do we get? If this is equal to R naught, of course, I'm assuming here that the plant does not have a pole at z equal to 1, otherwise we'd get perfect tracking, right? Zero tracking, zero error. Okay, so again, just like in continuous time, what we see is that as long as the plant has no poles or zeros at z equal to 1, then the steady state tracking error is going to depend on the value of the controller when you set z equal to 1. So as long as p of z has no poles or zeros at z equal to 1, ESS will depend on the steady state gain of the controller. Okay? And so the idea in discrete time is completely analogous to what we did in continuous time. We will increase the complexity of the controller to get a couple of extra parameters or tuning knobs so that we can simultaneously place the roots of the closed loop characteristic polynomial as well as adjust the value d of 1. Okay? So again, it's analogous. There's symmetry between continuous time and discrete time. So idea. And it's not an original idea. It's the same idea we had in continuous time. So we'll call it an idea anyway. Idea. Increase the order of d by 1 to simultaneously solve a pole placement problem and adjust the value d at 1. Okay. The difference here is we're going z equal to 1. In continuous time, it was s equal to 0, but same idea. Okay, so our controller then for an nth order plant, now the controller, previously it was n minus 1, 1 less than the plant. Now we're going to make it 1 more. So it's going to be nth order, same order as the plant, because we want to impose steady state tracking specifications. So our controller will look like this. Okay. I'll mention the same thing I said last time. I'm using a slightly different convention that I use for continuous time for the coefficients of the controller in the plant, right? The coefficients of the controller, I'm using the convention from chapter 6 in terms of the subscripts here, okay? So besides a slightly different convention for the subscripts on the parameters, it's the same as continuous time. Okay, so with this controller, the degree of the characteristic polynomial will be less than or equal to 2n now. So it's not 2n minus 1, it's 2n now. So we need to pick 2n desired z-plane pole locations. Okay. And just like continuous time, this will not completely specify all the parameters, right? There will be some extra degrees of freedom that we're going to use to do the tracking component. All right? So anyway, and use them to define a desired characteristic polynomial. Okay, and it's going to have order 2n. So I'm just going to write that down. Okay, so there's our desired characteristic polynomial. Okay. To get a last equation, we need one more equation to get a unique solution. So we're going to bring in the steady state spec. So to get an additional design equation, besides just matching coefficients between the polynomials, right? That, just like in continuous time, that'll partially define all of our design equations. We want this extra one to come from the steady state tracking. Use the ESS spec. Okay, and from the analysis above, assuming you've picked your desired pole locations to be stable, which of course you would, we want that this quantity be less than the maximum allowable tracking error. Okay. Just like in continuous time, what we'll do is we'll set it equal, and then we'll generate a parameter we'll use to adjust the steady state error. So this constraint is just, like only just satisfied if we get equality. Okay. I can rearrange that. -1. Okay. And so just like in continuous time, what we'll do is we'll take this quantity over here, and that'll define sort of a lower bound on what we want this number to be. Okay. So again, this looks very similar. So let delta be any real number such that delta is greater than this thing. So remember, this is given a spec. This is all given in the spec. So this is just something you can pick by knowing the specifications. You pick a delta bigger than that, and now we get, as long as d1 times p1 equals that delta, we will satisfy in steady state the tracking error specification. Okay, so then the steady state spec is met if, so let's write this out. So this thing should equal delta, right? So let's expand out the controller, right? The plant is just p of 1, you set z equal to 1, and you get a number. So d of 1 is the thing we don't know, right? The plant is sort of given from the model. D of 1 is we don't know yet because it depends on the controller gain. So I'm going to rewrite this as p of 1 times the sum from I equals 0 of all the controller gains. Remember, we're going to set z equal to 1 in this controller. So the numerator is going to be the sum of the g's then, and the denominator is going to be the sum of the f's. Okay, so I'm going to write that here. So we want that to equal delta. And so this is our design equation. Okay? I don't like the way it's written. I've got division by the f's, so let's rearrange. So I'm going to rearrange this to get something which looks like a linear equation. And I can write this as delta times the sum of the f's equals P1 times the sum of the g's. Okay, and this is the equation that we will add to our pole placement equations. So add this to our pole placement design equations. Okay, and I'll do it in the case when n is equal to 2. I'll write down what the equations would look like. So when n is equal to 2, what do those design equations look like? The following. We'll have to do an example next class, but let's write down the equations. So again, the thing we're trying to solve for are the controller gains. So I'll write them in this order. The right-hand side depends on the desired characteristic polynomial, so I'll write that over here. The last equation, I'm going to denote it with a bar, is going to come from our steady state specification. Okay, so again, this is again repetitive, but let's do it. The first column here comes from the denominator of our plant. So it's going to be 1, A1, A0, 0, 0. We'll stop at that green line. That last row is going to be reserved for this guy. So this guy is going to be in the last row. Okay. The first 5 rows are coming from pole placement. Okay. So again, denominator of the plant populates that, the coefficients of the denominator. Coefficients of the numerator I will use over here. So B0, B1, B2. So far, no difference in discrete time than continuous time. Nothing has changed. The only thing that's different here for the practical step tracking is this last equation. And again, I'm going to use this guy. And so what does this guy say? I'm going to write it as, let's bring this guy over to the right. So 0 equals negative delta times the f's. So I'm going to put negative delta over here. Plus the plant's DC gain, or steady state gain, times all the g's. So here we'll have P of 1, P of 1. Okay, and again, this is from the steady state spec, whereas the rest of the equations come from placing the poles. Okay. All right, I'm going to do an example now. Well, the next thing we're going to do is an example, but I've run out of time. I've got 30 seconds, so I will do an example of practical step tracking at the start of next class. All right, so we'll leave it at that. I guess the thing to take away here is that besides some superficial differences in the equations you get, conceptually we're doing the same thing. We're just doing it in discrete time. Okay, so keep in mind what is the advantage of doing this? Are the subscripts on the terms supposed to be ascending or descending in the matrix? So it's just like in continuous time. Okay, so again, in continuous time, it's the highest power generates the first coefficient. The next highest power generates the next coefficient, and the next highest power generates. Oh, this should. Oh, I see. There's a typo here. This should be A2. Yes. Good catch. Thank you. Yes, I assume that's what the question is about. Yeah, it should be. Yeah, it should be the same pattern as continuous time. There's a slight different convention in the subscript. So yes, sorry about that. My mistake. Okay, so it's conceptually the same thing, but what is the advantage of doing it in discrete time as opposed to emulation? Remember that the plant already has embedded in it the sampling period. The plant model depends on the sampling period. We are designing with the A to D and the D to A model embedded properly in the plant. Okay, so there shouldn't be any surprises when we go to implement. Okay, I'll stop there if there's any questions. Otherwise, I will see you tomorrow.